Hi, this is a short lecture video about derivative at gradient, Hessian, and function of matrices. Um, so this is going to be very quick, very tutorial video to actually review the concept of a function of several variables and how to compute the Jacobian metric, which is the first derivative, the Hessian matrix, the second derivative, and everything. We also would like to introduce you the function of matrices and, come up with a definition of first derivative of that function. Okay, from calculus, suppose we have a function that maps from Rn to Rm. This is called a vector value function because you have a variable that is in Rn, which means your f of x. Uh, your x is a vector x1 dot xn, but at the same time the value of your function is also a vector in Rn. So this is called vector value. Um, with that assumption, the derivative or the Jacobian metric of f at x is denoted by this notation is a matrix of m by n. Okay, where the ij entry of the Jacobian metric is actually looking at the ith component of f, take the partial derivative with respect to xj. Okay, for example, your fx, let's say your fx like this. Okay, your fx has two components. Okay, your fx has two components, but it's a function of three variables. Here in this example, f maps from R3 to R2. Okay, so the Jacobian matrix of f is going to be a matrix that has size 2 by 3. Okay, 2 by 3. Now the first entry of the Jacobian metric would be the derivative of f1, the first component of f, okay, with respect to x1. So it's 1. Okay, so here is 1. Now the next, the 1, 2 component here is going to be derivative of f1 respect to x2, which is also 1. Okay, and the last one is derivative of f1 respect to x3, so it's going to be 3x3 squared. Okay, now the second row of f is going to be the derivative of f2 respect to x1, x1, x2, and x3. So it's going to be minus 2 over x1 plus x2 cubed. Okay, the next term would be the same, minus 2 x1 plus x2 cubed. Okay, and the last entry here is the first derivative of f2 respect to x3, which is 0. Okay, very simple by the definition. This is the first derivative. Okay, or the Jacobian matrix. Okay, when we talk about a scalar value function, which is typically the case in engineering problem, so by that definition, okay, your f map from Rn to R, for example, your fx is the norm square. This is very typical, very common example. It maps from a vector x in Rn to a scalar value. Okay, in from the definition, of course, the Jacobian metric is going to be 1 by n. So it's going to be a row vector. So a lot of time people just use the term gradient. So what it means is that for the gradient is actually that the transpose of the Jacobian metric. So it becomes a column vector. Okay, so for the gradient of f, the ith component is actually the derivative of f respect to xi. Okay, now how about see a simple example. If your fx is A transpose x, this is a scalar value function. Okay. Your f map from Rn to R. Okay. Of course, your Jacobian matrix would be 1 by n. So the first one is you take derivative of f respect to x1. Respect to x1, of course, it is a1. Here, the second term you take derivative of f respect to x2, so it's a2, and so on. So the Jacobian metric is actually the row vector of A. And then the gradient of F is actually simple. It's just A. Okay. You see that this is a very obvious analogy. When you learn a function that map from R to R, if x is A times x, everything is scalar. Of course, the first derivative is simply A. Now you have a function that extend from a function of one variable to a function of several variables. So the definition of f is extended to A transpose x, and then the gradient is simply A. So very very intuitive generalization from a function of one variable to a function of n variable. Okay. Now I would like to make another example. How about let me put it here. How about quadratic function in x? Okay, here of course my f map from Rn to R. Here this is a very common notation that what I mean is that this is a vector of n by 1, and the matrix P is symmetric and is of size n by n. Okay, you should know that you can expand this quadratic form. Okay, so it's going to be x1 p11 x1 square p11 x2 square p22 ... xn square pnn. And now you're going to have all the crossing term, right? For example, so you're going to have what about p1 p12 x1 x2, okay, p13 x1 x3 ... p1n x1 xn. This is a crossing term between x1 and the other x. And of course you're going to have what, the crossing term between x2 and the other x. So it's going to be p23 x2 x3 ... p2n x2 xn, and so on. Okay, pn hold on, pn minus 1n xn minus 1 times xn. I hope this expansion is clear. You just you need to maybe review a little bit how to expand the quadratic form. And I hope you understand that the factor 2 here appears because the matrix P is symmetric matrix. Okay, just multiply this guy, and then you get this. Okay, now let's take a look. How about take the gradient? Okay, now the gradient of f, of course, is going to be a vector of n by 1. Okay, n by 1. How about the first row? The first row of f will be the derivative of f respect to x1. Respect to x1. So then you see that it's going to be what, respect to x1. So if I mark the terms that involve with x1 is going to be this, and this, right? So then you get p11 x1, right? plus p12 x2 dot 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 p1n xn. Okay, how about the second row? Maybe we move for we do it one more time with x2. Now I'm gonna mark with again I'm gonna mark the tail that involved with x2, so it's gonna be here, 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 and so on. Then you would see that it's gonna be what? It's gonna be p, actually here p12. Okay, p12, but p12 is actually p21 because p is symmetric. And then is p22 x2 dot 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 and p2n xn. Okay, dot dot dot. You see that the last term it would be pn1 x1 plus pn2 x2 dot 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 pnn xn. Okay, so basically this is this is what? This is p times x, the gradient of quadratic function in x. Okay, that is, has a parameter p. The gradient is actually px. Again, very intuitive. How about we looking at things when it is a scalar? How can of course the quadratic function when x is a scalar variable should be something like you have p that is scalar, okay, and you have x squared. This is scalar, a function of a scalar variable. Of course, in that sense, when you take the derivative, so it's going to be x times p. Okay, when things become vector and matrix, you see that the gradient become the matrix p times x, and that's the generalization from a function of scalar variable. Okay, now so that's a very simple and very common example. So here, what I would like you to do is that we're gonna encounter, we will encounter this type of function all the time. Linear in x, and also quadratic in x. So we don't need to compute the derivative or gradient, several times. So when we do it once, we just keep the form and just apply it immediately. Okay. Now let's move to second derivative. Okay, for the second derivative, we're gonna focus on the scalar value function only because it's simple. So for the second derivative, it means that so basically you need to take partial derivatives, second orders partial derivative. Okay. Suppose f is a mapping from Rn to R. We say that the Hessian matrix is denoted by this symbol, okay, and then it's like nabla square, but it is called Hessian matrix. So the Hessian matrix is going to be a matrix that has size n by n. Okay, and the ijth entry is going to be this, the second order partial derivative of f respect to xi and xj. You take the derivative of xj first and then xi. Okay, so you can think of the Hessian metric as the derivative of the gradient as well, right? Because when f maps from Rn to R, then your gradient is going to be a vector in Rn. Okay, so your Hessian metric is actually the derivative of the gradient again. Okay, so in this example, okay, that we just previously see, this is a quadratic function example. You know that the gradient is going to be px plus q. I would like you to make a, to make a note that we have a factor 1/2 here in the quadratic term because of what? Because when we compute this, when we compute the first derivative, you see the, when you take, for example, when you take the derivative of this guy, the power of 2 will be cancelled with 1/2. Okay, so that's why we have a factor 1/2 here, so that the gradient becomes, clean, that is only px. Okay, so that you don't have the annoying factor 2 all the time. Okay, now you see that the gradient is px plus q. Okay, and for px plus q, so it's going to be p11 x1, p12 x2, dot dot dot, p1n xn, and so on. Okay, plus q, this is a gradient. Then for the Hessian, as we said, that Hessian is actually, the derivative of the gradient. Now, so Hessian is going to be a metric that has size n by n. Now, for then the 1 entry, if you look at the first row of the Hessian, of course, it's going to be, the derivative of the first row of the gradient. But then with respect to x1, respect to x2, x3, dot xn. Now, if you see this, of course, the first term, the gradient, the derivative of the, of the green row respect to x1 is going to be p11. Respect to x2 is going to be p12, p13, and so on, p1n. And now you move to the second row. Okay, the second row of the Hessian is obtained by taking the derivative of the second row of the gradient respect to x1, which is p21, p22, p23, dot dot dot, p2n. And you just keep repeating this process, it's going to be what? pn1, pn2, dot dot dot, pnn. But remember that this p is symmetric. Okay, I explained in, one of the videos that when you consider a quadratic form in X, typically P is taken as a symmetric matrices, because if P is not symmetric, you can just take the symmetric part of P. Okay, so basically the gradient is simply the matrix P. Okay. So it's very, again, it follows our intuitive generalization. If your fx, when it is a function of one variable, suppose you have this, okay? The first derivative is px, and the second derivative would be p, okay? When you generalize things to vector case, okay, the Hessian metric is the matrix P that has size n by n. Okay. Now, a lot of time we're gonna see some, composite function. Okay, composite function. Your f map from so your f map from Rn to Rm. So your G map from Rm to Rp. In that case, your H is gonna be Rn maps to Rp. Okay, so then we say, everyone knows that, the chain rule, we're going to apply chain rule if you want to take the derivative of h. But because g and z are now both vector value function, then to apply chain rule, you need to be careful with the with the row of multiplication, because the Jacobian of g and f are both matrices. Then it appears it is a result that the Jacobian matrix of H is actually the Jacobian of G evaluate at F and then multiply with the Jacobian of F. Just like when we learn in calculus, if things are again function of is a function of one variable. So everyone know that the chain rule is this, right? Now we just realize it, that G prime becomes the Jacobian matrix evaluated at F for F prime. So it goes to extended to the Jacobian matrix of F. Okay. Now we talk about the special case of applying the chain rule. So if G is very simple, it's a scalar value function, and it's also a function of one variable. Okay, it means that the Jacobian of G becomes G prime. It's just a scalar. Okay, if F is Rn to R. Okay, now in this case, hold on. So it's going to be G prime multiplied with Fx and df, right? Df, apply the chain rule. But because F is a mapping from Rn to R, okay? And now your F is actually a function of Rn to R. Then, which means the Jacobian is a row vector. So if we, for convenient, for make things like more convenient, we just use the term gradient instead. So the gradient is the gradient is Jacobian matrix transpose, right? So it's going to be this G prime Fx and a gradient of Fx, because gradient of Fx is dFx transpose. Okay. So the little detail here is about gradient and Jacobian. Actually, in many other textbooks, they use these terms interchangeably, like they are the same thing. But I would like to make sure that I would like to make a note. I would like to make a clear explanation that. So that we don't get confused with the dimension and everything. Okay, we typically encounter a function of that map from Rn to R. Okay, and that's why we use the term gradient, and we define it such that it's a transpose of the Jacobian matrix, and so that the gradient becomes a column vector. Okay, but don't get confused if we in another place, like on the website or any other textbooks, you may see that people use the term Jacobian, but what they mean is a gradient, which is a column vector as well. Okay, so the Jacobian term is defined in a more general way because it's the first derivative of vector value function. Okay. Now let's go to some explicit example that we're going to see in engineering application. Suppose your H is a composite function of F with Ax plus B. So of course, this is an affine transformation. All right. So in this scenario, your H is like F of Gx, okay, where your Gx is Ax plus B, okay. So let's assume that your F mapped from Rn to R, okay. And of course, let's assume that your G mapped from Rn to okay, I can make a more general assumption. Let's assume that your F mapped from Rm to R, okay? So your G, in order, for this notation to make sense, your G, which is Ax plus B, your G mapped from Rn. N is a size of, it's a size of your X. G mapped from Rn to Rm. Okay, the output of G has to be a vector in Rm so that it becomes the domain of F. Okay, I hope it's not confusing. All right, then okay, if we apply the chain rule, of course the Jacobian of H is going to be the Jacobian of F evaluated at G, which is Ax plus B, and this is supposed to be what? To be the Jacobian of G, okay? But then if your gx is ax plus b, okay, of course, what is a Jacobian matrix? The Jacobian matrix is going to be A, right? Just expand this vector, matrix vector multiplication. A n n x n and a m1 x1. Okay, like if, of course, if you take the Jacobian of this guy, okay, this is a matrix of size m by 1. Your G map from Rn to Rm. So your Jacobian matrix is going to be a matrix of m by, sorry. It's going to be a matrix of n by m. Okay. Then you see that when you take the Jacobian, so it's going to be what? It's going to be A, right? Because why? Because of course the first row of the Jacobian is going to be given by, taking the derivative of this, okay, and then respect to x1, x2, and x3, and so on. Okay. I think I made a little mistake. Okay, the Jacobian of, okay, because G map from Rn to Rm, so the Jacobian metric is supposed to be, sorry, m by n. Okay, m by n. So this is going to be a11, a12, dot an, and am1, am2, dot amn. So it's simply a. Okay. Then we go back here. So this is a. Of course, the Jacobian of H is going to be 1 by m. Okay. Then if you use the term gradient instead, so that it's it's a column vector. So it's going to be A transpose, just transpose the whole thing here. So it's going to be A transpose gradient of F, AX plus B. Okay. How about the last example? Okay. The last example is this. Okay. It looks like some composite function. Okay. Now think about what would be the function f and function g. Okay, your f is supposed to be 1/2 x transpose px. Your gx is the vector value function. Okay, so if we just apply the previous result that that we just derived, okay, for f, the gradient of f, this is what we derived before, is simply px, and of course this is Jacobian of G is simply A. Okay, if we just follow this, the gradient of H is just A transpose, right, times the gradient of F, so it's P, right? But it has to be evaluated at G, so it's gonna be AX minus B. Okay, these two examples are very typical. We're gonna see a lot in in engineering problem. This is one type of a loss function that you see in a least square problem. So and of course we're gonna solve the problem, but as a solving optimization problem, then taking the gradient is one important step, because it gives us the optimality condition. So we're gonna encounter taking derivative gradient of function that has pattern like this all the time. So I hope that you come back to these two examples when we use it. Now I would like to move to a more general functions. Now we talk about function of matrices. So previously, this is a function of vector. Okay, the domain is, you know, Euclidean space. Now, a function of matrices, your X is a matrix of size m by n. Now we give us again two typical functions. Okay, first is a generalization of a linear function in X, a linear function in matrices. So for scalar is AX, for vector value is A transpose X. For function of matrices is trace of A transpose X. Trace is the operation that that only takes on you know, diagonal square matrix. Trace is a sum of diagonal terms. Okay. For trace of A, there are a lot of basic properties that you should know. Trace A and trace A transpose, they are the same. You have trace AB, it's going to be equal to trace BA. This is called the circular property. Trace ABC is going to be equal to trace CAB. Okay, and equal to trace BCA. This is called circular property. It's like you can move, you know, the rows of each matrix, and the traces are the same. Okay. What else do you need to know? Okay. Again, for scalar, for quadratic function in X, this is a function of one variable. For if it goes to a function of vectors, it's this, right? Now, for a function of matrices, is extended to trace of X transpose AX. This is quadratic in X. So the dimension of A, we haven't defined here, but just so you know that A can be a matrix of size, you know, of some size that can make the whole thing valid, can make the whole thing make sense. It doesn't have to be square. Okay. Now the definition of derivative, you know, when a function is a function of matrices, is very simple. We talk about scalar value function only, because otherwise it's going to be too complicated. Okay, the definition is the following. We just take the derivative of f respect to each entries of X. So the Jacobian is going to be a metric of size m by 1. Okay. The differential of f can be generalized to the following identity as well. So when you make a perturbation of X, okay, dx means a very small perturbation in X, so that, you know, X plus dx is still in the domain of f. Okay. Now, fx plus dx minus fx, it should be, you know, a linear, an inner product between the Jacobian, the first derivative, and the with the perturbation dx plus higher order term. So this identity is nothing new, but actually the Taylor expansion. I hope that is clear to you that fx plus delta x, if things are scalar, okay, you know that this is going to be fx plus what? F prime, right? F prime what? F prime times delta x, okay? And what else? What else? If you go to the second order, it's going to be F double prime x delta x square, right? And go on, so on. This is actually a Taylor series, but for Taylor expansion, so you're gonna have some remainder term, right? So now if we talk about first order Taylor expansion, it means that you are only interested in the first two terms. It's linear with the delta x. So we call, you know, the rest of it as what? a higher order term. Okay, so this is called first order Taylor expansion. Now, if we extend it to a function of vector, you have seen it before. The Taylor expansion is going to be the following. Now, x is a vector, so it's going to be fx plus the gradient of f transpose delta x. Okay, again, plus delta x transpose Hessian of f delta x and dot dot dot. Again, you see that you see that if you compare these two terms, the purple one, you're going to see that delta x is multiplied with the first derivative of x of f evaluated at x. So when it goes to a function of vector, so this multiplication becomes inner product, an inner product between gradient vector and delta x. Now delta x is a vector, gradient is also a vector, so inner product, we call it inner product. So it makes sense that when you extend it to a function of matrices, okay, this term actually represents inner product between the gradient, the Jacobian matrix, and the perturbation dx. Now I use the term, I use the symbol this is an inner product associated with some inner product space that is of your interest. Now, if you work with matrices, okay, if of course Rm by n is an inner product space, the inner product in this space is going to be this. A inner product with B is actually trace of B transpose A. Okay. So by this notation, so here, so it's actually trace of dx transpose del f by del x. Okay. So now with this first order Taylor expansion, it gives us a practical way to derive and to recognize the derivative, the first derivative of a function of matrices. Now, let's see. Simple example. Linear function in x. Of course, we have seen function of vector, function of scalar before. Okay, we know that for scalar, if it's linear in x, the first derivative is going to be simply a. If it's a vector, if x is a vector, we use the term gradient, the first derivative, and the gradient is a vector a. Now you would think that when we generalize it to a function of matrices, somehow the first derivative of this f should be something related to a only. Okay, now we're going to figure out what would be the first derivative. Is it a, or should it be a transpose, and things like that. Okay, now very simple, we go by the definition for this one. The first derivative is simply, take the partial derivative of f respect to all xj. Okay, x11, the first row is going to be, with respect to x11, x12, dot dot dot, x1n. Now we use the fact that, trace of a transpose x, trace is the sum of diagonal. So this is by the definition of trace. Okay, but secondly, you know that when you multiply two matrices, okay, so the II entry of A transpose X is going to be the sum of A transpose Ki, X Ki. Okay. What's next? or this is supposed, this is wrong. Okay, so this is supposed to be xik. Okay, right? Like if C is AB, okay, Cij is ABij. What is it? It's going to be the summation of AIK BKJ, right? For all KA. Then A transpose X II. So it should be A transpose, sorry, this is wrong. This is IK times XKI. But because A transpose IK is actually AKI, right? So basically, for example, if my X is 2 by 3, okay, so this is just sum of, A11 x11 plus A12 x12, okay, and A13 x13, and next is going to be A12, oh sorry, A21 x21 plus A22 x22 plus A23 x23, and that's it. Now, the first derivative is going to be a matrix of size m by n. So it's going to be 2 by 3. And how do we get this? Just take derivative of this guy respect to the first row, respect to x1, which is A11, respect to x2, respect to x12, which is A12, A13. So very simple. So simply A, the final result is simply A. Okay. Now, if we would like to derive derivative by using, by deriving the Taylor expansion and try to recognize the term that make the inner product with dx, that's going to be our Jacobian matrix. Now, let's take a look in that approach. So, fx plus dx minus fx. So this is x plus dx minus fx. Okay. Next, you're gonna see that the trace operator, it has a linear property that trace of a plus b is gonna be trace a plus trace b. Now, so trace of ax, this term and this term will be cancelled, and now you're gonna have a trace of a transpose dx at the end. Now, it is in the form of what? It is in the form of some metric transpose, trace of some metric transpose with another matrix. All right. So it's actually the inner product of, and it is the inner product of what? Dx and A. Okay. If you have space of Rm by n, okay, the inner product between A, B, which is trace B transpose A, is going to be the same as the inner product between B and A, because this is the property, one of the property of inner product. Okay, and you can see it by the trace property as well. These guys are equal. Okay, so then this is an inner product between dx and A. Then we can read, all right, so we can just recognize that, okay, the difference between, the function of, perturbation, minus fx is going to be something, inner product with dx. So that thing should be the first derivative, and that is A. Okay, finally, we have the same result. Okay. So now let's move on to a more, maybe more complicated. So here it's more complicated because it's quadratic in X. Now you don't want to expand this function in terms of xi and xj. Now I'm gonna use the first order, Taylor expansion approach. So again, I'm gonna compute fx plus dx minus fx. So by the definition, of course, x plus dx minus fx. Now let's expand this term. Okay, now I'm just gonna multiply everything out. So it's gonna be x transpose ax plus x transpose a dx plus dx transpose ax. Plus dx transpose a dx. Okay, this is the first term. When you subtract from trace x transpose ax, now you're gonna have this, okay, and this, okay. So the green term is this, but then you see the orange term. The orange term is dx transpose a dx. So it is like quadratic in dx. Okay, so that's why in the second line, I just extract only the term that is linear in dx. Okay, and I consider this term as a higher order term. Now, trace of a x transpose a dx. Okay, the first term here is actually trace of a transpose x dx, right? So it's the inner product between dx and a transpose x. Okay, now the second term is trace dx transpose ax. Of course, is the inner product between ax and dx. Then I just read that, of course, if you combine the whole thing, so it's going to be inner product between dx, with a transpose x plus ax. And that's why we read that the Jacobian matrix is A transpose X plus AX. Okay, makes sense? This is quadratic function in X. So the first derivative should be a linear in X. Okay, now let's see this example. Suppose your fx is y minus xh Frobenius norm square. Frobenius norm is simply trace x transpose x. Okay, Frobenius norm is just, you take all the entry of xij, okay, square, and then just that, okay, just sum square of all the entries. It's a generalization of two norm to a matrix. Okay. Now, given this function, can you find the Jacobian matrix with respect to x? Okay. Now we say, because now first the Frobenius norm, you change it to so the Frobenius norm of y minus xh is going to be trace of y minus xh transpose y minus xh. Okay. Now you compute fx plus dx. Okay. So you're gonna have dx times h. Okay. Now you're gonna subtract from. You're gonna make a subtraction from fx. Now I would like you to take a look at this term and expand the whole thing. Now how about we make a grouping, okay? And now if you see that if you multiply this with this and then take the trace, it's actually fx, right? And now you just consider next, you just consider the linear term in dx. So you're going to have what? H transpose dx transpose, right? And this guy would be multiplied with this, y minus xh. Okay. And the next linear term should be this guy transpose this. Okay. So it's y minus xh transpose times dxh. Okay. Now the remaining is just the step that I'm just gonna arrange. We just arrange the term in the second line so that you know you see conceptually that the second line is just a linear function in dx. Now we just need to write it as inner product between dx with something, and that rectangular, that's something that we need to figure out, will be defined, should be our the first derivative. Okay, now let's do it. Okay, now the first, let's take a look at the first term. Okay, trace of this. Okay, of course, trace of this. Then you use what? You can use the fact that this is the circular property. Okay, you just move this guy to the front. This is circular property. Okay, and then from this one is what? This one is also equal to the trace of, if you transpose the whole thing, it would be the xh y minus, hold on, okay, sorry, never mind. So this guy, if you take a look at it, it looks like you take the trace of dx transpose and again y minus xh h transpose. Again, circular property, but that is in the form of trace of something with triangle. So it's supposed to be the inner product between dx and y minus xh h transpose. Okay, the first term, again, it goes the same way. Okay, if you have this, the green box, so this is equal to, I try to write it as something transpose dx. Okay, and that should be y minus sh transpose h. Sorry, wrong. So it's supposed to be y minus xh times h transpose and transpose again with dx. Okay, so then I figure that it is the inner product between y minus h transpose and dx. Okay, then I combine the two terms. Okay, I combine the two terms, and then so you get a factor of -2. Okay, the two terms are the same. Okay, see, yellow terms are the same. So you get a factor of 1, 2, and you read that, sorry, you get a factor of 2, and you can read that the term in the yellow one, the yellow color with the factor 2, is actually the gradient of this function. So it looks very intuitive as well when you have the norm square. All right, so it's like the first derivative should be this term, and then you need to apply the chain rule because h multiplied with x. But the way the chain rule applies is that you have h transpose on the back of this expression. Okay, maybe it looks very complicated at the beginning, but what I try to represent here is actually a really function that you will see in application, especially in the green one is actually a quadratic loss where the variable is a matrix. We're gonna see it when we, for example, when you consider a vector autoregressive process, and we would like to estimate its parameter, which is going to be a matrix. Okay, so this is a least square loss function. Okay. Next, and should be the last, log det function. We go back to, scalar case. Okay, if f(x) is defined as a log x function, natural log, what is the first derivative? Of course, it's 1 over x. Okay, now I would like to extend to, a function of a matrix f mapped from symmetric matrix to R. Of course, in the scalar case, the domain of f is R++, only positive value. It's going to be in the domain of log x. Now, when we generalize to a function of a matrix, we say, let's define fx as a log determinant of x. And the domain of f is actually the set of positive definite matrices. Because for positive definite matrix, you know that all the eigenvalues of such matrices are all positive. So the determinant, which is the product of, eigenvalues, will be positive. So it would make sense when you take the log. I mean, we're gonna, because we want to restrict our function to be real value. Okay. Now we're going to use the same approach that we're going to consider the first order expansion of the log determinant function. And then we're going to recognize the term that take the inner product with dx, linear dx. But now it may be, in this example, I would like to show some, mathematical trick, okay? Log of determinant of x plus dx. Because in order for this to make sense, we're gonna we're gonna put x in the domain, and we make sure that dx is a metric in such a way that the whole thing is a positive definite as well. Okay, so if x is positive definite, then of course it makes sense, it's valid that x must have square root. If you don't know what it is, you watch the video of how to factorize a positive definite matrix in many ways, okay? So the square root of a matrix is actually, a matrix that, multiply with itself and it gives the original x, okay? Square root of x can be obtained from eigenvalue decomposition. Okay. Now, which means I can make a factor of square root. Okay, I factor it out, pre and post. Then I need to compensate here with dx with the inverse of x, inverse of x square root. Okay, I hope it's clear. Okay, just this. Okay, and then I say I factor out x1/2. Okay, here is going to be I, and here is going to be inverse. Okay. Now, next, in the second line, what do you know about, it appears like 3 terms multiplied together. So you know that the property of determinant is what? The determinant of ABC is the determinant of A, determinant of B, determinant of C, right? So it's going to be determinant of x1/2, determinant of x1/2, and the rest. But the determinant of x1/2, x1/2, so it's actually determinant of x, okay? And you use the fact that the log of the product, right? The log of the product is going to be the sum of log. So that's why you have plus here. I hope it's clear. Should I explain a little bit more? Of course, okay, from this line, so it's going to be log det x1 half, det x1 half, det I plus x minus 1 half dx x minus 1 half. Okay, and then because this is actually det x, and then when you take log of the product is the sum of log, and then you get the second line. In the third line, we use the fact from matrix analysis that if you just look at this as, you know, as a matrix M, okay, what do you know about determinant of I plus M? First of all, determinant of a matrix is actually the product of eigenvalue of M. This is one fact. The second fact is that the lambda, the eigenvalue of I plus M, is actually 1 plus lambda of M. Okay, this is another fact. Then determinant of I plus M is going to be the product of 1 plus lambda M. Okay, now if you take the log, of the product, so it's going to be the sum of log. Okay, so this is the sum of log 1 plus lambda I. And lambda I denotes the eigenvalue of this guy, of this M. Okay, now you just subtract this from this, and then this is fx plus dx minus fx. Now we're going to use another approximation from calculus, and again from Taylor series, Taylor expansion. You have log of 1 plus lambda. Okay, now we can use the fact that the first order, you know, the first order Taylor expansion about zero, log 1 plus x is actually x when x is small. So this is actually Taylor expansion about 0. Then this term is approximated by the summation of lambda I. Now, another fact is that the sum of eigenvalues, okay, trace of M is actually the summation of the eigenvalue. All of the properties here are basic property from, you know, eigenvalues when we learn linear algebra. So if you forget, please review. Okay. Now, for this step, in this step, the summation of lambda I is then, of course, by the trace property. It's actually the trace of that matrix. It's the trace of that matrix. And now you use the circular property. So you can move x minus 1 half to the front. So it becomes trace of x inverse dx. From here, you can again figure out that it is an inner product between dx and x inverse. X is symmetric. So with or without transpose, it's the same thing. Now you can see that now you can, you just read it off, recognize that the first derivative is x inverse. And now you can see that it makes a lot of sense. It extends from a function of you know, one variable. You take derivative of log x, you get 1 over x. When x becomes a matrix, the first derivative of log that x is x inverse. Okay, so this is I give you several common functions of matrices and explain how to derive the derivative by using by trying to make a similar similarity between the term that will involve derivative, which is the inner product with dx. Okay. So I would like to end the video. If it's not clear, we will come back with more examples in the online course. So this concept will be used in many lectures of mine in system identification class, in optimization, and other things. Okay. All right.